In this video, I want to take a look at the equation of spheres, just gaining a little vocabulary of how three-dimensional objects can be represented by equations in three variables. So a sphere, as you know, or as you may know, is the locus of points in space that are a given distance away from a given point. That's sort of the geometric definition. So give me a point and give me a distance, and then I want everything that is that distance away from that point. And I'm really shaky with my drawings. In the plane, that would be a circle, but in space, it's it's a sphere. And I draw the sphere as poorly as, as best I can there, which is pretty poorly, trying to give it some 3D depth by putting an equator in there. It might be easier if I said, oh, look, here's a sphere, right? And here's a sphere that I can look at from different angles. Okay. So the point in the center of that sphere would be the dot that I drew, and then let's go back to here. The center of the sphere would be here, and then every single point on the sphere is the same distance away from that point. Now we have a way of measuring distances. So for instance, if I put the center here at the origin, so every point on the sphere, x, y, z, has a distance away from the origin of d. Well, if I think of that as a vector, if I think of x, y, z as a vector based at the origin, then the length of x, y, z is exactly its distance from the origin, right? Because in standard position, it's got one end at the origin. So I know that the length of the vector x, y, z is, I'll use 2. The length of x, y, z is the square root of x squared plus y squared plus z squared. And now, if I'm saying that I want all of the points whose distance away from the origin is d, then I'm saying I want the square root of x squared plus y squared plus z squared to equal d. And I could leave that as the equation of the sphere, but generally it's not written that way. We square both sides, and we say x squared plus y squared plus z squared is equal to d squared, right? Notice that this is very similar in the plane to the equation of a circle centered at the origin, where x squared plus y squared equals, usually we say r squared, where r is the radius. Well, r would be the radius, in this case d is the radius, although we usually use d as diameter, but in this case, because it's the length, the distance from the origin, and I called it d, it is the radius of that sphere. So if it's centered at the origin, this is what the equation looks like, center at origin. But if the center is somewhere else, then the equation is going to look a little different. So let's say now that I've got some point out here in space, x1, y1, z1, and I want all the points a given distance away from that. Let's call that distance r this time. Let's call it radius r. And so I'm going to have this sphere centered at that other point out there like that. Well, I can find the distance between these 2 points in a very similar way that I would find the length of a vector. Right? Well, actually, there's a couple ways I think of it. I want to start thinking in terms of vectors. So a point on the sphere is going to be the point x, y, z. If I think of it rather than a point, if I think of it as a vector based at the origin, and I think of this as a vector based at the origin, then I know that the vector going from one tip to the other tip is the difference of those 2 vectors. Okay? So this black line segment here, I could call that the vector xyz minus the vector x1, y1, z1. Okay? End minus beginning. So that vector there is what I want to have length r. Well, that vector, if I simplify it and I subtract those 2 things, I get x minus x1, I get y minus y1, and I get z minus z1. So that would be the coordinates. If I stuck that vector in standard position, it would be right here. This point would be x minus x1, y minus y1, z minus z1. And I want the length of that to be r. So the length of that is square each of the components, so x minus x1 squared plus y minus y1 squared plus z minus z1 squared. And I want that equal, well, I want the square root of that to equal r, so I want this to equal r squared. So if it's centered at the origin, it's essentially x minus 0 quantity squared plus y minus 0 quantity squared plus z minus 0 quantity squared. If it's centered at x1, y1, z1, then there's the x1, there's the y1, there's the z1. And of course, there's the radius right there. So equations of spheres are reasonably easy to write down if you know the center and you know the radius. So there's situations that come up that you might consider, like what if you knew, rather than the center and the radius, what if you knew the two endpoints, right, of a diameter? Let's say I got a sphere here, and I know that this point and that point are the ends of a diameter going right through the middle. So let's suppose this is the point 1, 2, 3, and this over here is the point 4, 5, 6. Can we come up with the equation of that sphere? Well, to come up with the equation of the sphere, I need to know a center and a radius. So I got to find the point in the middle, and then I got to find this distance. Well, to find the point in the middle is kind of interesting. Again, I think in terms of vectors. This is something you got to learn how to do. I've got some coordinate system somewhere, and if I think of those two endpoints, this one and that one, right, as vectors, look at the picture on the side here. If I've got two vectors like this, I know that if I add them up, it gives me this diagonal. This is u and this is v. Then this is u plus v all the way out there. I claim that if I cut that in half, I will get the point right in between those two. That if I take u plus v and divide it by 2, these are all vectors, that's going to be this point, that's going to be that vector right in the middle. Now, how do we know it's right in the middle? Well, from geometry, I know some things like the diagonals of a parallelogram bisect each other. Right? That is, where the two things intersect, the two diagonals intersect, bisects both of them. So bisect means cut in half. So add them up and divide by 2. Well, this makes a whole lot of sense to me. You know, if I have two numbers, 7 and 13, and I want to know the number exactly in the middle, I take the average. I'd add them up and divide by 2. 7, 13, add them up to 20, divide by 2, 10. 10 is right in the middle. If I've got two vectors and I want to find the point right in the middle, I just add them up and divide by 2. So here, I would take 1 plus 4, 2 plus 5, 3 plus 6, and divide that whole vector by 2, which is going to be, what's that, 5 divided by 2? 5 halves, 7 divided by 2, 7 halves, and what's that, 9 divided by 2. So the point in the middle, which is the center of the sphere, has got coordinates like that. Now I need to know what the radius is. Well, the radius is the length between the center and one of the edges, or it's half the distance all the way across. Let's find the total diameter there. So to find the distance all the way across, how am I going to do that? Well, there's a box, right? That we have 2 points in space. We can look at what's the difference in the x coordinates, what's the difference in the y coordinates, what's the difference in the z coordinates, and then I want that diagonal from one all the way across to the other, right? Well, that's just this length squared plus that length squared plus this length squared. So I need to know the difference in the x values. Well, the difference in the x values is 4 minus 1. The difference in the y values is 5 minus 2. And the difference in the z values is 6 minus 3. So I think that's 3, 3, 3. So if I look at the length of 3, 3, 3, actually this vector would be 3, 3, 3. So the length of that vector is going to be 3 squared plus 3 squared plus 3 squared. Square root 9 plus 9 plus 9 is the square root of 27. So now I know the radius of my... No, that's the diameter, isn't it? That's the diameter. The radius is going to be half of that. So the equation of this sphere is now going to be x minus the x-coordinate of the center squared plus y minus the y-coordinate of the center squared plus z minus the z-coordinate squared equals the radius squared. Well, the radius is the square root of 27 over 2, so when I square that, it's going to be 27 over 4. And there's the equation of the sphere, knowing the two endpoints of one diameter. Okay. We took the average of those 2 points to find the center. We then used, we used the 2 points to find the length of the diameter, cut it in half to get the length of the radius, and then plugged it into the equation for a sphere. The thing that I really like about vectors is that they allow me to do things with geometric objects that are very similar to what I already do with numbers, right? How do you find the point halfway between here and there? Well, think of them as vectors, add them up and divide by 2. How do I find the number right in between two numbers? Add them up and divide by 2. You take the average, right? And there's a lot of things like that if I can think of using vectors like numbers, their algebraic properties are very the same, right? They're very much the same. You can add them in any order. There's a distributive property, there's an associative property, there's all these things. There's all the algebra of them is just like the way numbers work. And so I can do a lot of stuff in geometry that I already know how to do with numbers.